Hello everyone, before we start with problem solving, today I'm going to show you some preliminaries with some useful mathematics. If you look at a natural process of either a growth or a decay of a quantity, and that quantity will be changing by a constant fraction of itself, it can be described as following: dn over n equals plus or minus, the plus is for the growth and the minus is for the decay, times some constant times times dx. If that is in space, it could be also dt if it's in time. The exponential series e to the power x is equal to 1 plus x squared divided by 2 factorial plus x to the power 3 divided by 3 factorial and so on. If you had a constant next to the x, then you just substitute cx instead of x, and you get 1 plus cx all squared divided by 2 factorial and so on. So we can take the derivative of the exponent with a constant c here. So we have c times the same exponent. You can take the second derivative, and then you would have c times the first c, and now we give you the c squared e to the power cx. J is defined as square root of minus 1, and this is the identity, the Euler's identity, cosine x plus j sine x equals e to the power jx. We can describe a sine x also in terms of a series, so it would be x minus x to the power 3 divided by 3 factorial plus x to the power 5 divided by 5 factorial minus x to the power 7 divided by 7 factorial and so on. And you can do something similar with cosine x, and what you notice is that for the sine x, it's basically the terms that you see here in the exponent. It would be the second, and then the fourth with a minus sign, and then the sixth, and then the eighth with the minus sign, and so on. And for the cosine, it would be the first, then the third with a minus sign, then the fifth, then the seventh with a minus sign, and so on. So we can show this actually if we write e to the power jx. What is e to the power jx? I can substitute j instead of the c here. So I have the following: 1 plus jx plus jx all squared divided by 2 factorial plus jx to the power 3 divided by 3 factorial and so on. Noting that the j squared would give me a minus sign, the j to the power 3 would give me a minus j in front of the x to the power 3 here, and j to the power 4 would give me twice minus sign, so it could give me a plus sign. So the 6 here would give me a minus sign, and this here would have a plus with a j in front of the x to the power 5. So if we do that, this is what we get: 1 plus jx minus x squared divided by 2 factorial and so on. Now you can collect the terms. The first, the third, the fifth, and the seventh would give you the cosine. This is exactly what you have here. And the second, the fourth, the sixth, and so on would give you j times the sine. And this is what you get here. Okay, so this is the Euler's identity. Okay, so it is sometimes useful to write cosine x in this form, in an exponential form. So it's e to the power jx plus e to the power minus jx divided by 2, and sine x would be in a similar way e to the power jx, but with a minus sign here, e to the power minus jx divided by 2j. So we have a minus sign instead of the plus, and you have a j down here. When you're superposing, for example, waves, this can be useful. You have a cosine omega t plus a cosine omega t plus some delta, and then you add to that a cosine omega t plus 2 delta, 3 delta, and so on until you get a cosine omega t plus n minus 1 delta. This can be written in this form: a sine n delta divided by 2 divided by sine delta over 2 times cosine omega t plus n minus 1 divided by 2 times delta. And you can make use of the complex exponential notation. So you type for the same thing ae j omega t power j omega t plus ae power j omega t plus delta, and then you add the third wave and the fourth wave and so on, and you get a times e to the power j omega t times 1 plus z to the power 2 plus until you get z to the power n minus 1, where z is the e power j times delta. Okay. Now, if we write s as 1 plus z squared until z to the power n minus 1, then z times s would be the following until z to the power n. So you can write sz now as a function of z, so it would be 1 minus z to the power n divided by 1 minus z. If we go back to the using the definition of z, it would be 1 minus e to the power j n delta divided by 1 minus e to the power j delta. So if we had a, this is the wave, a e to the power j omega t, but the superposed wave, times s of z, that would give a e to the power j omega t times 1 minus e j n delta divided by 1 minus e j delta. And with a little bit of work, we finally get into this following result, which is basically the same as the result that we had here. Just now we have it in with an exponential notation. Alright, so the last thing I wanted to mention today is about the complex conjugate. So if z is a e to the power j omega t, then the complex conjugate would be a e to the power with a minus sign here, j omega t. So it's easy to work out the when you have z times z conjugate, that would be a e j omega t times a e minus j omega t. So we have a times e j omega t minus j omega t, and this gives 1 squared here, right? A times a squared. So you have a squared. This is also very useful when we deal with waves. Alright, that's all.